Welcome to the course on game theory in the autumn term 2020 at the University Mannheim. This is the second video of week 11. Now finally we come to interesting examples. All the examples in this section are taken from the book of Walter Schlee, but for the first and most interesting example he cites himself the book of Holler and Illing, but in an older edition. So the first water example is rather concrete. We have four communities who are the players, 1, 2, 3, 4, and they all need a new water supply system. And now we will list the costs for the communities if they work alone or if they work in some coalitions. So the communities 1 and 2 are close to one another, and also communities 3 and 4 are close to one another. And generally, if communities work together, it's cheaper. They have some synergy than if they work alone. So here we get a cost function for any coalition, the cost function for the new water supply system. And here the table lists the values of it. So for any coalition B, any subset of the set 1, 2, 3, 4, C of B is the cost of one water supply system for all the communities in the subset B. And one unit may be, for example, 100,000 euro. So here you see a table. Unfortunately, I cut it off on the right hand side. So for the coalition 2, 3, 4, this value is still 6. And for the total coalition 1, 2, 3, 4, the value is 7. So here 1, 2, 3, 4, 4 here gets the value 7. So one sees the synergy. If any community works alone, the costs are 3 units. If the communities 1, 2 or 3, 4 work together, the costs are 4 units because they're close to one another. If 1, 3 or 1, 4 or 2, 3 or 2, 4 work together, the costs are 5 units because these pairs of communities are not so close to one another. If 3 communities work together, the costs are 6 units, and if all 7 work together, the costs are 7 units. So there's a clear synergy. The more work together, the better for all of them. So, but this is not yet a cooperative game because you have this cost function, but now by the sign change, I get immediately a cooperative gain. So minus the cost function is in the coalition valuation V. Now there comes a non-trivial claim. It's surprisingly hard to prove. I claim that this cooperative game with minus cost function as coalition valuation is a convex cooperative game. So from the definition we know that one has to see that for any two coalitions B and C, subset of A, the sum of their coalition values is lesser equal than the coalition value of the union plus the coalition value of the intersection. So if now this is translated to the cost function, then the cost for each single coalition B and C, the sum of the cost functions for the coalitions B and coalition C must be bigger or equal to the cost function for the union plus the cost function for the intersection. So in order to prove that, one has to do quite a lot. The easy cases are the cases where one coalition is contained in the other. If B is subset C, then B union C is equal to C and B intersection C is equal to B. So then we have equality. And similarly, if C is subset of B. So these are the easy cases. There's nothing more to do. But we have lots of other cases where both coalitions are not empty and not the full set, and they are not contained in one another. So we have cases where they are disjoint, but we have also cases where they are not disjoint. And on some extra sheet, I prepared now a handwritten note with a table of all the essential different possibilities. And this table is long, and I don't see any other way than to go through this table to prove this claim. So here you see the beginning of the table. In this example 613. So on the left, in the left 2 columns, we see this coalitions B and C. Then the costs for B, costs for C, costs for the union, and costs for the intersection. So if B consists of player 1, C consists of player 2. Each has the cost 3, 3. The union has the cost 4, and the section has the cost 0 because the section is empty. 3 plus 3 is bigger or equal to 4 plus 0. This fits. And the same for the other cases. So here we have also the case 1, 3. 3 plus 3 is bigger than 5 plus 0. The case 1, 3 and 4. 3 plus 4 is bigger than 6 plus 0. The case 1, 2 and 3. 3 plus 5 is bigger than 6 and 0. The case 1, 2, 3, 4. 3 plus 6 is bigger than 7 plus 0. The case 1, 2, 3, 4. 4 plus 4 is bigger than 7 plus 0, and so on. So and below there come some cases. So here we start with the cases where the collisions are not disjoint. So 1, 2, 1, 3. 4 plus 5 is bigger than 6 plus 3. 4 is bigger or equal to 6 plus 3, namely equal. And then 1, 2, 1, 3, 4. 4 plus 6 is bigger or equal to 7 plus 3, namely equal. So in some of these cases we have equality, and in all we have a non-strict inequality, so this game is really convex. But the bad point is I needed a long table, compare many different cases to prove this. I haven't listed all cases, but I've listed essentially all cases. So if I compare two collisions with only one, each with one member, I can restrict to the cases 1, 2 and 1, 3, because 1, 2 are typical for the two communities which are close to one another, and 1, 3 is typical for two communities which are far from one another. So I don't get other numbers if I look at other pairs of them. So in that sense, my list is optimal, but it's still quite long. There are quite many cases in this list. So this is not a difficult proof, but it takes time. It's completely elementary, but it's some work. So some more statements. The theorem 610a, because of convexity, tells us that the core is not empty. And theorem 610b tells us especially the core consists of the imputations which are not dominated. And now I make another claim which can be checked by hand. I claim that the core contains the following 8 vectors. So first I claim these are imputations, and further I claim they are in the core. To show this, one has to see that for any collision B subset A, the sum of these values of these vectors, of each of these vectors, is less or equal to the cost for this collision. My core meant that the sum of the values of the minus this vector must be bigger or equal to the value of this collision. So here the other sign, so the sum of the Zi must be less or equal than the cost of this collision. And one can check this if we look at the table. So any one player for one single player we have the values 1, 2, 3, which are all less or equal to 3, which is the value of a one player collision. For two of the numbers Zi, we get the value, some value 1 plus 2 or 1 plus 3 or 2 plus 3, but 2 plus 3 I get only if I don't look at the pairs 1, 2 and 3, 4. So for the pair 1, 2 and for the pair 3, 4 I get at most 2 plus 1 or 3 plus 1, which is 3 or 4, which is less or equal to 4, which I need. For the pair 1, 3 I can get the values 3 plus 2, which is 5, but it's also allowed because the collision 1 and 3 has a cost 5. So now for collisions with 3 players I get values between 4 and 6, which is fine because the cost function there has value 6. And for the complete collision of all 4 players I get always exactly the value 7, which I need because this shall be an imputation. So one checks this. Now I checked essentially by hand that these 8 vectors are in the core of the game. So, and later we will return to this example and we will see that or minus the core of the game. So that minus the core of the game is the convex hull of this set. So Lemma 67b told us that the core is a convex polytope. And because it contains these 8 points and it contains also their convex hull, that's the easy part. And theorem 618, which will come in section 6.3, will tell us that the core is the convex hull of this set. And I will return to this example in example 619. So I will not discuss this more now, I will discuss this later in section 6.3. So, but there's also some serious work to prove that the equality here. So now the core is one solution concept, but in fact the 4 communities really want to split the costs, and what is the best and fairest way to split the costs. And for that one needs a Shapley value, or the Shapley-Shuby index. But here, because of symmetry, the result is quite easy. Here the fairest and best distribution of the costs is even share. So each has to pay 7 divided by 4 units. So they have to divide it into equal big parts. So this follows from the symmetry here, which is not so interesting, but one gets it also by applying the formulas for the Shapley value. And I will return to this, I think, in example 627. And the Shapley value will be discussed in section 6.4. So this was a rather concrete example. Now there comes just some small, another example. In the moment, I just want to model some situation by some cooperative game. So the situation is the following. We have 3 players, and player 1 can produce a basic product with some positive value A. Player 2 can do nothing alone, but he can improve the basic product of player 1 to a final product with value B, which is bigger A. And player C also can do nothing alone, but he can improve the basic product of player 1 to a final product with value C, where C is bigger or equal to B. And B and C together can't do more than player 3 alone. So that implies now that we can model the situation by the following cooperative game. We have the 3 players 1 to 3, and the collision valuation is given by value A for player 1, value 0 for player 2, value 0 for player 3, because alone they can't do anything. Then value B for the collision 1, 2, value C for the collision 1, 3, value 0 for the collision 2 and 3, and value C again for the collision 1, 2, 3. So this is a cooperative game with 3 players, and in a moment I will make some general discussion of cooperative games with 3 players, and afterwards I will come back to this example. That will be example 617. But before, I want to give still one other rather trivial example. It's here. So if you look at a 2-person game in 0-1 reduced form, there is not much, because then the collision value for any 1-person collision is just 0, and the collision value for the 2-person collision is here, the total collision is of course the value 1. So this game is then unique, and of course it is convex, and one sees also one sees that it's convex, and one sees also that the core in this case consists of all the vectors with entries Z1, Z2, such that these entries are non-negative, and such that their sum is equal to 1. So here the core is isomorphic to the unit interval from 0 to 1. So so that means in 2-person games are not so interesting. Any essential 2-person game can be reduced to a 0-1 reduced form, and that is unique. So there's not much to do. In the case of 3-person games, the situation is much more interesting, and that will come now in this next example, but that will be in the next video. Thank you very much for listening to this video.